All right. Welcome back. Hope you had a good Posca. I know we all enjoy that nice vacation in the springtime. I certainly do. I certainly do. And I'm back. It's Steven. It's Dr. Steve and my companion, Bo, here is with me, ready to lead the lesson today. So here we go. So first thing, actually, before I get into the actual lesson, I actually think I should mention that I have put up the third exercise, and today's lesson is all about doing the third exercise, basically. And I'm just going to quickly pop it up here. I'm not going to go through it item by item, but I just want to make you aware of it. Here we go. There we go. Come on. Let's do it. There we go. And a little bit more. Yes. And up here. There we go. Come on. There we go. All right. So this is the next graded exercise, number 3. And I just wrote this in the last few days. I have done the solution. But there's always, going to come up questions or uncertainties or unknowns when you do something for the first time. So don't be afraid to ask me about this exercise, but I did really try to make it clear, and I did really try. I put quite a lot of time into it, actually, but there's always something. There's always something still that's maybe not clear or not, is missing or something. So please let me know. Just in case you're curious about language and things, from here on out, I think I'm pretty much doing everything in English. And the course, the final exam is in Danish, but next year the course, or actually this fall, the next cycle, and we switched the schedule of this course to fall after the next cycle, the course switches to English. And the logic behind that is, we have an English textbook, we have English references, we read English papers, all the software documentation is in English. It's too much to try to switch and to translate back and forth and to try to keep control over all this and to make sense of it all. So actually the course itself actually does become an English course starting with the next academic year.
Can I ask about the exam, Stephen?
Yeah.
So is the exam the same exam from exams from last year, or how are they being done now that since they're being made in Danish and not English?
Well, I have a censor, and my plan is I write the exam and I send it to the censor and I say, hey, fix the grammar. So I'm pretty confident that the Danish exam will not have grammar mistakes in it. So I will write the exam and send it to the censor and say, hey, would you look at this and correct my speech or correct my writing? And so, so that won't be a problem. We'll make sure that the text of the exam is correct from a language point of view.
Perfect, thank you.
Yeah, because we don't want to mess that one up. It's a lot of stress if there's something wrong in that respect. But and then next year I don't need to worry about that anymore. I would have just switched the exam to English, but by the regulations of the school, I can't do that because we listed the course in Danish, so I got to do the exam in Danish. And I'm not going to do 2 exams like we did in the midterm because that creates its own set of problems, and it just got too much. So anyway, so here is the exercise, and it's all about stepwise and subsets regression, which as you're going to find out today, is great big, huge area. I mean, it's a lot, and a field where there's not really always one correct answer. But looking over here at the page, pretty standard stuff. Again, please, I need you guys to format your responses so that when it displays on the screen, it's one page wide, so that I see it on my screen when I'm grading it. I can see it and look at it correctly. That's really required. And then a little bit longer description here. So this exercise is based on a published paper on some railway, on an Italian railway data set. It's based on delays, analysis of delays on the Italian railways. And so the data set for this exercise is a portion, is a subset of the data from this paper. So you're actually working with some real data here, and which is related to a real published research paper. It's pretty, I hope after today's lecture, the instructions for this are pretty clear. 6 questions, and the scale is basically 1 question, 1 point, basically. And as I did for the last assignment, a partial correct is half a point. So one question, 1 point, and partial correct is half a point, and that's how I'm going to grade these. So 6 questions is 6 points, and then the assignment's worth 6 1/4. So you get a 1/4 point for formatting the report correctly or something. Basically, if you get 1 question right out of 6, you get 1 1/4 points, and then from then on, it just goes up in 1 point increments. We'll just kind of do that. But anyway, I take a look at this during the pause or whatever. I think after the lecture, this all falls directly with what we're going to do in the lecture today. So hopefully after the lecture, everything is like, yeah, I know what I'm doing. So I just want to let you be aware of that. So I'm going to close that, and let's get started here. Let's get started with the material. I have no idea how long this is going to take. My hope is that it's short. My hope is that this is done in 2 hours, and then you have time left over to kind of get started on the exercise. Well, let's see. It might even go faster. It might even be just an hour and a half, maybe. It depends on how much discussion we have. So let's see what happens. Here we go. Let me get the right window in the right place here. Here we go. So here's what we're going to talk about today. We're going to talk about something called the, this is Japanese. I have no idea how to pronounce this. This is Japanese. The Aic information criteria. We're going to talk about that. And then we'll demo software and code for the stepwise method and the subsets method, and then have a little short comment at the end on data transformation. And then we're done. And that should cover all the material you need to do this exercise 3. So here's what your textbook talks about model building strategies. It's on page 97 of your text. Not a lot. It's like 2 pages. Woohoo! That's not a lot, folks. I'm a little disappointed in that. That's kind of, that's like the guy got tired and went to bed early and said, I'm done. I don't want to do anymore. But what's in this slide here is pretty much the way I was taught to do this long ago, like in the Stone Age, when I still had hair on my head. This is how I was taught to do it. And I still have my old textbook up here. This is my textbook. This was my university textbook for regression. And it's a really good book, by the way. I kind of like to use it next year. But So when I went to plan, and this is pretty straightforward here, and we'll go over this in more detail here. Stepwise, you pick some quality measure and then you step through the variables and keep adding one or subtracting one until the model no longer becomes better, and then you stop. And then there's a whole, we won't learn this, but in my book up there, the actual equations are in there for you to actually, it's almost like the simplex method in linear programming. And you may not know what that is either, because maybe you haven't had that, but you have a set of choices, you do some calculations, and you get values for each of the choices, and then you pick the one with the best value, and then you go forward. And that's what stepwise is. You have a bunch of choices of variables, you calculate the values for all those variables, you pick the best one, you pick it, you move forward, repeat. And so that's how stepwise works. And then best subset is you just fit everything. You just do all the possible model combinations, make a table of all the models, read through the table and say, yeah, that one. Truthfully, that's, that really is how it works. And that's what I learned, basically. All done, right? No problem. I figured I'd pull out my books, pull out the software, and have this whole lecture done in a day. And then like enjoy Easter, Not wrong. No, it did not happen. No siree. Man, I put a ton of time into this lecture. A lot of late nights, a lot of work, because wow, a lot has changed in the 15 years since I really learned this the first time. A lot has changed, a huge amount. And what really came up, how this really happened is, I went into the R software, and then I went into the support materials for the R software, and then I started getting the documentation and putting together the code, and suddenly all kinds of stuff started showing up in the documentation and in the software that I had never heard of. Never heard of it. Never. And I was like, wow, what is going on here? What happened to all the things I learned when I was in school? Where'd they go? And the answer is they're gone. The answer is it's in 15 years, the science and the math and the ways of doing this have changed enormously since when I learned this. And a lot of that has been driven by the computing power. There are methods we will do today in this lecture that realistically you could not have done when I was in school, because they require an enormous amount of computing power, and you didn't have it 15, 20 years ago. The laptop I'm using today to teach you, it is so much more powerful. I think I still even have it in a closet in the house. I have my old laptop from my PhD days, and it's a great big thick brick, and when you fire it up, the fan goes, the technology has changed so much, right? And I'm going to get a new computer, new laptop even now here in this weekend from DTU that is going to be even a scale of factor faster than this one I'm using now, because this one I'm using now is the one I got when I started working at DTU in 2014. So the computing power has exploded. And so things that we just never even considered doing 15 years ago, it's like, yeah, let's put it in the software. So here's one of those. So here's what we're talking about. Here's this thing called the Aic information criteria is brand new to me. I had never heard of this, never. And yet it is the central, most popular, most important criteria in all of the software I looked at for doing regression. And it does not exist in this book at all. It is not in here. And it is only mentioned on one page in your book, and it has not, and on the page it's mentioned, it's not even talking about stepwise regression. So this is new, and it's new, and yet from the Google searches and from the literature and from the papers and from the software, this is it. This is the current most popular and most recommended method for doing this stepwise criteria search. And I don't know anything about it. I mean, other than what I read on Google, on Wikipedia. So I'm not actually in a position to like answer all kinds of deep questions about this formula because I was not trained with this. But I mean, I could figure it out. I'm sure if I spent another, 12 or 16 hours reading papers on this, I'd have a deeper understanding. I just didn't have time to do that in the preparation for today's lecture. But we are going to use this, and it is central to the software we're going to use, and we're just going to have to like accept that it's okay. We're just going to have to go with what the documentation says and say, yeah, we trust it. It's okay. Because I don't have the ability to judge it, to tell you whether it's wrong or right. It's so new. And it's an example also of how technology changes and how science changes, because this Aic information criteria, which is abbreviated AIC, it's not new in the sense that it just got published last year. It actually was this fellow here in the photo. I don't even know if this guy's still alive, but this fellow in the photo actually published it in 1973. So it's not new in that sense. It's 50 years old, right? It's 45 years old. But as is very common, is very typical, it takes a long time from when somebody first invents something and proves it in the academic research, in the literature, until either the tools or the software or the methods or the computers grow to the point that they can do it. And that's also true, for example, with linear programming. Linear programming was invented, proven in papers mathematically by people in the late 1930s. And it was used actually in World War II for a lot of critical planning problems like food rationing. But for the rest of us, for business, for teaching in schools, basically you don't see it until the 1960s. And really not a lot. And then really not until the 1970s. And even then it's really basic. I mean, really small models that are, done on paper. So it's really doesn't explode as a method until the 80s and 90s, when the computing power and the tools come to be available. So anyway, so this is what we use. This is the criteria that is the most popular that we will use in most of our software commands. It does have some mathematical relationship to things I did learn. So for example, there is, under one particular set of settings, AIC can be the same as something called Mallow's CP, which I did learn, which was part of my regression lessons for like 15 minutes back in the day. It wasn't central to our methods because we used a different method. But it has some mathematical relationship to existing older methods. But it really is something new on itself. And so here is, I just copied this from Wikipedia. This I thought was a well-written piece of text and pretty much gives a good, clear explanation. And notice, notice that I highlighted in yellow here. I think one of the reasons that AIC is so popular is because it balances some of these things I told you earlier before POSCA. So remember, before POSCA, I said, hey, we want a good model. We want a model with a high R squared, but we don't want to just throw everything into the model. This isn't a garbage can. This isn't an FL-SPAN. We don't just like throw everything in and get as high in R squared as you want. We want a balance between model size and the model R squared, and we want a balance here. And so if you look at the calculation of this AIC, it contains a value for the size of the model. So it is balancing the measurement of the model with the size of the model. So I think this is one of the reasons why it's so popular, because it introduces into the decision this balance between complexity and performance. I think those are the correct words that I should choose. Complexity and performance. And the AIC balances that in a better way than many of the other measures. For example, p-value. P-value doesn't control for complexity. It does control for performance, I think I would argue. R squared controls for performance and doesn't cares not at all about complexity. So you have these different factors here. But anyway, so that's what I can tell you about AIC, but it is central to what we're going to do today in the software. It doesn't solve everything. AIC does not just solve everything. We still have to use our brain. We still have to look at the reports. We still have to look at the printouts, because we still could have two different models that have similar AIC numbers, and we can just look at the residuals, or we can look at the plots, or we can look at some other factors and say, yeah, but this model's better, or something like that. So it's still not the kind of thing where you can just turn on the software, push the button, and walk away and say, I'm done. Software solved it for me. No, you can't do that. So we're going to continue with this data set from last time. So pull out that data, go get it. Same data set, and we want to use it in the final form that we had it last time. So we want to use it with the transformations, the functional class transformations that we did. And so pull that data set out, pull that out. And it should look something like this. So this is what the data set looks like. Is he okay? Just checking on the dog. He's fine. He's happy. So this is what the data set should look like. And pull that out. And we want to now, we're going to do this. We're going to run this stepwise regression right here. So we're going to use a package called mass. Also, remember when you boot up R, remember to delete your old work. So when you quit R, all of the work you did actually gets saved. So you want to make sure that you don't, I don't know, maybe it's not a problem, because I think when you write a command and you say create some object, and if the object already exists, I think R just overwrites it. I'm not sure. I haven't actually tried that, because I have personally made an effort to always delete everything before I start over. But anyway, to be safe, anyway, for me, I just delete everything. But you have to manually do that. You have to go in and say RM parenthesis, delete the stuff I want to delete. So I will show that here in a minute. But we're going to use this mass package. And these are the code lines that we would call. Now, I've obviously already imported my data. These are the code lines we would call. I found a neat little trick as I kind of get warmed up and get my skills going here with R. If I want to just throw the entire data set into the model, I don't have to type every name from the data set into the model. I can just type the period. I can just type tilde period, and that means take everything. That means do everything. And so that's mighty convenient here. So so this is the code. And in a minute here, I'm going to open my R window, my R software, and then we'll run this. Let's do this together. I'm just kind of taking a drink here and pausing while everybody warms up, gets their R software running, gets their data file out. All righty. So I'm going to start my R software. Let me get the menu here. Yes. And let's boot this. Come on. Here we go. Yes. Yes. Here comes the window. All right, now I need to move this around on the screen a little bit. Let's move that there. Let's move this over here. And do like that. Okay, I'm going to make that window a little bit bigger there. There we go. All right. I could probably, I don't know if it makes a difference. I'll move it over here. Most of the text is limited to just this left 2/3 of the window. All right, I'm going to move this window over here. I'm going to hide that window. Good. All right. Good, good, good. All right. So let me start tip tapping with the keyboard here. Clear the screen. Let's see what else is, what did I leave out here? See, this is all the stuff. So this is all the stuff I was working on the last couple of days, last night, in preparation for today, and it's still sitting here. It's still in the software. I'm going to delete it all because I want to start clean. I want to start clean here for today's presentation. So see how fast that went? That's what happens after you've spent 12 hours doing this. After a while, you get really good. So that's what it takes. Practice, right? I mean, that's how you bottom line. So now I look at it and now there's nothing, right? So now I got nothing. So let's clear screen. Let's start over. Okay. So let's pull this data in. Let's pull this data in, and I have it in, remember, this is a really good idea. Oh, I wonder, I bet, what do you think's gonna, I think this is because I quit R and I reopened it. I think I'm gonna get a message here in a minute. Let's try this. I think this is gonna give me an error, but I just want to do it for fun to show what is gonna happen. So there's where I've got my data, V2 version 2, because I changed it from last time. Yeah, and if you ever wonder what this number is right here, that's which tab you want to import from the spreadsheet. So if you have a spreadsheet with multiple tabs, you just, the first one is number 1, 2, 3, 4. So if you just change that number, you can import the data from a different tab, just in case you're curious. So let's see, I bet this is going to say no. Yeah, I knew it would. So I haven't loaded my Excel package yet. Oh, and there's a fun new command. I don't have to go to the menu to do that. I can just go library, Excel, SX, and boom, there it is. There it is. So now I've loaded that package. I haven't installed it. The installation, you still got to go up to the menu and install it. But if you've already installed it, you just need to load it. Library is your command. Library is your buddy. So let's do, and little up and down arrows allow me to recall code from the previous time. That's mighty handy. And bloop. And there we go. And there's the data. Data's in there. And another couple other fun commands I learned that you might like too. Aims, whoops, that was a mistake. Come on. Come on. I did something. I hit the wrong key and now I can't get out of it. Out of here. There we go. Let's try this again. And yeah, see, that's a fun command. That just tells you what the columns are in your data file, in your data frame. It's called a frame in R, a data frame. Who thought that one up? Jesus. All right, so head. This is a fun command. If you just want to see the first few, if you have a really big data file and you just want to see the first few lines, this is great. This is really helpful. So now it just gives me the first 10 lines. That's really nice. It'd be really useful because the data set I gave you for the exercise is like 5,000 rows. So I don't think you want to print all that to your screen. So good. So we have our data. We're good with that. And now I told you I need that mass library, which I believe is a default installation. I don't remember. I don't think I had to manually install it. I think it comes with the standard R package, but you'll find out when you call this command. So we're going to load that. So boom, it's in. You got it. And now let's run this. Let's do a stepwise. Now, I posted documentation with your exercise, lots and lots of documentation. And there are lots of extra commands that you can put into the step AIC command, extra options, but you don't, they're not absolutely required all the time. But so for example, in step IAC, you can choose forward, backward, or both. And what both means is that at each step of the loop, it checks to see, can I add something? And then it checks to see, can I remove something? And so it does one of each at each loop. Add, remove, add, remove, add, remove. What's that noise? Oh, never mind. I heard something's going on down in the basement. So the default for step IAC is both. So if you don't say anything, it's going to do both. And a bunch of other things are default, so you don't need to specifically type them in as commands. And you can see all this in the documentation. The problem with stepwise forward is that in order to do it, you need to start with something called an empty model. And that there's a little trick to making one of those that I haven't shown anybody. If you really feel an urge to do that, you'll have to read the documentation yourself and figure that out. Anyway, here we go. So I want to create a regression. First, I need to create a full model that we're going to put into StepFit, into Step AIC, and Step AIC is going to loop around and take out things from this model. So here we go. I got to get that little tilde character. Come here. Let's do this. Come on, mister. How should I do this the easiest way? Whoops, I'm going to just exit this. There we go. That's easier. That's easier. Yeah, that's going to work. Copy and paste for today is the way to go. My data. Yes. Yes. And that's good. And then, so that has created the full model as just a random general linear regression model with every variable in it. And now we're going to run the stepwise and see, oh, excuse me, I'm going to sneeze. Oh, okay. So here we go. So now we're going to do the step process. So I want to create a different data result, a different, well, it's a data frame, essentially. It's an object, step fit, which is the results of this tool. So I'm going to run the step AIC process on this all fit model. And it is going to do this loop and look for a better fit, a better model that has less complexity, but achieves a good AIC score. So let's do it. Woo, bang, there you go. And this is actually pretty impressive. Just in case you want to know, this is actually pretty good because, in the old days, SAS would have kind of chunked and churned and actually taken a little bit longer to drive through this window. So what's going on here? Let's take a look at this. So it starts here, and we have the model. Now the data set has 9 variables in it. So right now we start with 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the full model here in the first step. This is the full model here in the first step. And this model has an AIC of 2310. Now, there's something here I have to say I could not find documented that is really confusing. The primary references, Wikipedia, and the other software we're going to use later in today's lecture, those references say that a smaller AIC is a good thing. But this piece of software, when it runs very clearly, and in the documentation, very clearly says AIC equals some number, sorts the variables in ascending order of AIC value, and removes the smallest AIC. So this piece of software right here it appears to be trying to get a higher AIC number. I haven't found the documentation of why what is going on here. I don't fully understand. This is an example of, where the literature and the books, the textbooks haven't caught up. So I'm not clear what the logic is here, but for this software, it says, here's the AIC right now. It prints out the model's variables and sorts them in order. What this number is here is a kind of a contribution. It is the contribution of each variable to the AIC. And here we have a sum of squares number, and here we have also the contribution of each variable to the sum of squares regression. And so the one at the top, locale, is got a very small sum of squares. So it has a very small contribution to this model. It's a very small contribution. Might even be p-value. This does not show the p-values. So we don't, and there's probably a command that would tell me that, but I don't know what it is, to be honest with you. I mean, that's how new this is. But what's going to happen here is at the next step, it's going to say, hey, let's increase this cutoff for the AIC and delete the variables that are outside that cutoff. So down here, the AIC has been increased or changed to, well, the scale changes too with the next data set, which is a little confusing. But here, the next step has gone to 230809. That's actually lower than this number, but in relationship to the table of values down here, notice these values have changed too. So it has changed this cutoff, and that has eliminated locale from the list. And so now the list is recalculated with a whole different set of values. And it repeats this again. It goes down here. It sets a new cutoff for the AIC, and then it cuts something out again. And it keeps doing that. So it keeps doing that down the line here. So we're getting smaller, 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 and we're done. And so and it stops here, and this is kind of its best model based on the AIC criteria. So it has stepped through the model, and at each step, it has looked at this AIC number and said, which of these variables is not really a great contributor to the AIC, and I will take it out. Now, what we did not see here, but I have seen this in my studies and in other data sets, and it could happen in a more complicated model. What we did not see here is, in this case, we started with a full model, and it got smaller and smaller and smaller and smaller. What we did not see is we did not see this model get small and then get large again. And that can happen. That can happen. It could be with a data set that, it pulls out a variable, chick, 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 comes down, and then it says, I changed my mind. Let's put one back in again. So, and it could go up again. It could start to add the variable back. And sometimes in a really bad, it's possible in a really bad situation, it gets into a loop where it takes something out, puts something in, and then cha-ching, and then it goes to the next level, and it's like, oh no, let's take it out again, put something else in. And it can get in a loop where it just take out, put in, take out, put in, it just keeps going and going and going, and it doesn't stop. That can happen too. I've seen that with like some sample data sets that I had in my regression class when I was a student. But anyway, so now this has got a solution. It's got a best model. So let's take a look at the analysis of that. So the command for that, if we go step fit $, ANUVA, boom. This is the summary of what just happened. So we started with this model and we finished with this model. And this says final model, but it's essentially the best model as well from this process. So this is what we finished with. And down here is a summary of the table of data from that best model right there. So the next thing that we might like to do is actually see that model. We might actually like to see it, you know, the whole deal, coefficients and p-values and everything. So let's do that. I got that. I got that. And here we go.
I think there's a question, Stephen.
Yes. Yes. Where are we? Where are you? Where are you? Here we go. Here we go. And oh, you're gone. Oh, there you are. And well, come on. Window. Little pop-up window keeps. There we go. And oh, thank you for researching that. Yeah, I kind of figured he wasn't with us any longer. Yeah, so the AIC. So let's from the Jonas, from the perspective of what is AIC, or how is AIC being used in this model?
Yeah, how it's being used. That's
Yeah.
how I should have formulated it.
So let me tell you where my confusion comes from. So here's the definition from Wikipedia. And the definition says the preferred model is the one with the minimum AIC value, right? And there's a software package we will use at the end of the lecture where that is clearly what's happening in the software. But in this example I just ran, and in the manual that documents this code, that's not what I see happening here, because what's happening is the ones with the higher value are staying in the model and the ones with the lower value are getting cut out. And I don't have an explanation for that. I honestly do not. I don't get it. I don't know what's, I mean, it's buried somewhere in some deep technical report or paper about this software. I honestly don't know. In this package, the mass package with step AIC, it is calculating an AIC value, and it may not be the same AIC value. I think what's really happening is, I think it says here at the top, it says AIC, but it may not be, there may be different kinds of AIC is my point. There may be different kinds of AIC, and this may not be the exact same AIC as the one we just looked at in the Wikipedia paper, in the Wikipedia article. So it's a little, it's a quality measure. And if you had taken this course, if I had taught this to you 10 years ago, we would have run SAS. And in SAS, the quality measure would have been, in most cases, would have been the p-value. It would have been a stepwise process where it looked at the p-value for the variable and it deleted the one with the worst, with the worst p-value. That's the way it worked when I did it. And that seems to be in the literature and in the documentation largely replaced by AIC. So.
Okay, thank you.
Yeah, I'm sorry, I don't have a better, but I know enough to at least that I trust this is correct. I know enough that I think this is correct. And so it's you know, and I've run enough of different examples, I can see it churning away and I can see the results coming out. And the results do roughly correspond to what would happen if I did the stepwise by pulling on p-values. But they're not always the same. It's not always the same. Sometimes it's different. And I think that I think what it means is that the people, the academics, the really hardcore mathematicians like my good friend Bo Fries over at DTU Compute, they have decided that this is the way to go. They have looked at this backwards and forwards and said, hey, AIC is our choice. And I probably could ask him, you know, I could probably ask Bo Fries, and you know, he could probably explain this or something, but I haven't had the time. I don't want to bother him with, you know, non-important questions from his perspective. Anyway, so this is a summary of what it did, and this is a summary of the last result. And so now we would like to actually get the model. So what we need to do, let me just move this little window here so I can see what I'm looking at. Okay, there we go. Good. All right. I'm going to cheat. I have the code actually written in the slide. I'm going to cheat and copy it from the slide. Oh, no, I can't. I made a picture. I have to type it. I'm going to have to type it. Okay, here we go. Best model. Linear model. Oh, I can copy this. I can. There we go. This will work. That's how I did it last time. I can copy that and paste it down here. That works. My data. And that's correct. Yes, that's correct. And let's go. And so run. Okay, and now let's see what the result is. This is same code we used last time. This is not new now. This is review. And that's correct. And so this is it right here. This is what you get. This is what the model actually is complete from StepIC's recommendation. And you can, and just looking at the screen at this model right here, not a lot to complain about. You know, I like it. It looks great. You know, it looks pretty good. All of the variables are really significant. These little stars on the right, they're like, they're like Expedia's travel recommendation, right? You always want 3-star or higher, right? So these are all highly recommended. These are all very significant. The p-values are like nothing. The p-values are 0. And very good p-values. We have an R-squared of 80%, 81% here. So have a nice R-squared and very good p-values. And, you know, if you remember from last time, without this tool, we were just fooling around, right? I mean, you know, we spent an hour last week before Easter, and we just randomly picked models and then printed out the results and said, hey, how about this one? Then we tried this one, and then we tried that one. This thing in 45 seconds went straight to, yep, this is it. There's the answer. Now, is there a better answer? Is there a different answer? We will find out. Okay, maybe there is, but the difference is really small. We're really, really close here. So, and let's see the plots. Yes. And yes. So here we go. So here's the plot. There's the residuals. Not bad. Not bad. There's clearly still a pattern in these residuals. There's clearly still a pattern, but I think this can only be resolved by further data transformation. There's some more variables in here that could be converted to class variables, to qualitative indicator variables, like we did with the functional control, or the functional, it was not functional control, it was I forget what we called it. FC was I can't remember. Anyway, the FC variables. There are a couple of other variables that really are qualitative like that we could switch, that we could change. But you know, this is pretty good progress here. I noticed something in this residual chart that I haven't found the documentation for. And it's there somewhere. I just don't know where. That's one of the negatives about, you know, I've said this before, one of the negatives about using R and open source software is there is no customer support and there's nobody being paid to write documentation. And you have to really dig sometimes to find out how something really works. And you have to use a lot of Google, a lot of different sources. But anyway, I'm pretty sure that these numbered points are outliers. And I'm pretty sure that these are outliers that are being selected by some method such as the hat matrix, which we haven't talked about. And in fact, we may not have time to talk about because of where we're going. But something called the hat matrix, which is in your book, which is a way of calculating a statistic that recommends whether a data point is an outlier or not. And so what appears to be happening here is that this software is purposely numbering these points because the hat matrix or whatever other method they're using to test for outliers indicates that these might be outliers. And so it could be, and these are the row numbers in the data set. These are the row numbers. So this is data row 64 and data row 65 and data row 71 in the spreadsheet. So what this means is if you really wanted to go further and investigate this, yeah, we'll take a break. We'll take a break after this. You could take the spreadsheet and delete these rows or manipulate it in R, but take the spreadsheet and delete these rows and then rerun the model. And it could be that the model changes significantly because these outliers are influencing the model significantly. But otherwise, it's a pretty good residual picture there. Here's our normality alignment. So just to review, what is this picture? This picture is a statement over whether our residuals, whether our error is normally distributed or not. And clearly we have some severe divergence from normality at the upper and lower ends of the data set of the residuals. So that's an indicator for, you know, the data is not normally distributed, which is a very common problem. And you know, there are ways we could deal with that. We could switch to a regression method that does not assume normality of the data and such, but we will not have time, I don't think, to do that in this course. So, and then I'm not gonna talk about that. So we're done. So those are the figures. And I think, yes. Yeah, this is the place to take a break. So would you take a break here? 10-minute break and we'll see you back in a little bit. I will not forget this. Hello, I'm back. And
Steven,
yeah.
Can you send the data set you're working with if we didn't have it from last time?
I think it's on D2 Learn.
Sorry, not the data set, but you know, didn't you like fortolket on these data, translate these data into something? We did it last time, right?
Yeah.
If we haven't done that, because we made it on one computer, not on all three.
Yeah.
So is there any way you can send what you're working on right now so we can join in when you're doing it and try making it ourselves? Oh, it's shared file. Thank you, Kirsten.
This is currently where we at. I've read it in our studio and sent it.
Okay. Thank you.
Is that fine? I mean, that's a good point. Let me.
That's
I don't
perfect.
remember if I.
Because the old file is on, or the non-formulated file is on D2Learn, but not the
Yeah.
one you're, yeah.
And this script is changing, transforming it. So yeah.
Thank you.
Yes. All right. Okay. All right. I put it up as well. All right. Good. All right. So we before the break, we had this up on the screen from R, and go back to slides here for a little bit. So we have a nice R squared, and here is where we were before Easter, before Posca. So this is where we were before Posca, and so all of the results on this screen are not from today; they are from last time. And you can see there's just a little bit higher R squared here from our random made-up model we did ourselves, but the significance level on the variables is horrible, right? We got lots of variables here where the significance is not very good. So even though it has a little bit higher R squared, in my opinion, this is a worse model, and it uses more data, more variables, and it's maybe not as accurate, maybe not as reliable. So so that's just give you a sense of, before and now. Then we already looked at this picture, and we already looked at this picture, and wham, here we go. So now we're ready to do another method. So let's try best subsets. Now I experienced this, so be careful. I experienced this actually while doing the solution for your homework problem, that with best subsets, it's possible to make some bad choices and send your computer into an infinite calculation loop, to which the only way to get out of it is to escape or to quit the program. So be careful about that. So I have only recommended using the various genetic algorithms, or the various more high speed, less accurate solution commands to avoid that happening. But so I mentioned that a main reason we're able to do this is because our computing power has grown. But whenever a problem grows exponentially, then it doesn't matter how much computing power we get, we won't be able to solve them just by brute force. That's not going to happen. That's not going to happen. And we see that in linear programming a lot too. There are problems in linear programming that effectively cannot be solved to optimality in any reasonable amount of time. I mean, there are problems in linear programming that very quickly require hundreds of hours of programming if you truly want to get the absolute optimal solution. And that's clearly not acceptable in most business applications. So we have heuristics and other methods and genetic algorithms and stuff. So the number of possible regression models, combinations of a regression model, is 2 to the number of variables. So the highway data set we're using right now has 9 variables. So there are 512 possible regression models. And that number, I think I mistyped that. Let me check that. I think it's 524. I don't know why I wrote 512. I think it's actually 524. Let me just check my math one more time. 2 this 9 equals, no, that's correct. I don't know why I was thinking 524. It's correct. 512 is correct. So anyway, so 512. So that doesn't sound too scary. It's a lot. It's enough to fill a number of printed pages, but it's manageable. But your homework data set has 30 variables. So at 2 to the power of 30, that is over a billion. That is over a billion models, right? So that's why my computer went into an infinite loop, because I hit the button and I said, calculate all. And it was just going and going for like 6 hours. I went to dinner and came back and it was still going. And it only got to like 200,000. So yeah. So you have to be careful about that. So that's why this is an area of active research, and that's why this is cutting edge and new, because you just can't brute force calculate it. You have to use intelligent methods. And so let's take a look and so that like AIC. And so let's take a look at some of these intelligent methods. So we're going to look at 2 ways to do subsets regression. Why? Because I found them. Because I found 2 software sets. There are more. There are more. There are more methods. There are more software packages for R. There are many more, actually. And but these 2 seemed reasonably well documented, seemed reasonably popular, and seem to have some good examples online. So so this is what I decided to use. Hold on a minute. I can hear my son. Hey, bud. I can hear you when you're teaching. Sorry about that. All right, so leaps. So leaps is maybe not as advanced as the second package we're going to look at. Leaps seems a little bit older and a little bit less powerful. And its selection mode, the default selection mode, seems to be R squared. I could be wrong. I didn't have the time to really research this deeply, and you know, as it typically is with R, the documentation is spread out all over the place. And very often, I found very often there are things that are not documented in the quote official documentation that you only find by like reading people's conversations on Stack Exchange, you know, or something, which is a bulletin board conversation area for programmers. So that's kind of a little bit above our modes here for teaching. But anyway, so this mode is looking to maximize R squared. And so here's the code. And the only key comments to make here is there's a factor called number of best. So what it does is this code is going to generate, it's going to look, well, let's start with NV max first. NV max says, what is the biggest model you want me to fit? And so in this case, I set it to 8. That means this will only fit models with up to 8 variables. And this is an important feature because it can happen that you will get error messages or problems in large models or weird things going on. And sometimes you can make those errors go away by reducing the value of NV max to less than the whole data set. So here our data set has 9 variables and I set NV max to 8. So I'm basically saying, build me a model with something less than the full data set. And within each number of count of variables, I am asking this software to give me one solution. So it could be there are 2 models, for example, with 4 variables each that are really good. But when I set nbest to 1, it will only return one of those models. So I only get one model for each level of count of variables, which I think is perfectly reasonable because at some point it's just too much. There's too much information. There's too much to manage. You just need something. You just need to damp it down. You just slow down. Don't give me so much. I just want some key information here. So this is the code. So let's run this. So I'm going to switch over to R. And there's the R window, and there's that window, and that's good. And I'm just going to clear the screen. Whoops. Come on, click in there. There we go. Clear the screen. And there we go. Okay. So we need the leaps library. Oh, wait a minute. I'm not supposed to do this. You are. This one I do want you guys to do. I've got, because we went through one already with the previous example. You've got the code right here on the screen. Let's go here. You've got the code right here on the screen. I think you're clever enough that you can just do this. So actually I had proposed that this be a do-it-yourself activity. So let's do that. So I'm going to set up the breakout rooms, and it shouldn't take very long, I guess. It maybe so maybe it'll go pretty quick actually. So let's just say 5 minutes in a breakout room. And there are, yes, okay, so 3 breakout rooms. And let's do that. That's fine. Yeah. So like 5 minutes, and do this. And then I'd like one or more of you to share your screen and show me what you got out of this model, and we can talk about it. I have the solution on my slides as well, but I want to get you guys active in doing something. So I've been talking the whole time. So anyway, go for it. Go for it. And if you don't want to hear my music, then you got to join a breakout room, because then you won't hear my music while you're in the breakout room. But if you're out here and not in the breakout room, you're going to listen to my music. And turn that off. And what do you got? Somebody share something. Can you hear me? Let me see. I got the mic on. Yeah. All right. Yeah. So Milal, what do you guys got?
It didn't really work. I think I wrote it wrong.
Let's put your R window up on the screen and let's debug it.
Yeah, sure. It might flicker and then we'll see, just like last time.
Well,
it's a
that's
little
too
bit
small.
small.
Can we close some windows or move stuff around or something? I can't see it. See, which is the main window? This one in the lower left?
This one, yeah,
okay.
Lower left.
And I don't know if that window works. Let's see if we could go a little larger in the font. Can you make the text bigger?
I don't think so. I don't know how to do that.
Okay.
Actually. Let me just try to make it.
I may not be on that control. I imagine that RStudio has a function for changing the text size, but I could try that. That's one way to do it.
Is it better now?
Actually, that works. It is yeah, that's better. That is better. Yeah. All right, let's see here. What is it? What is the error message you're getting? Could not find. Okay, it can't find the function. There's no package, so you need to install the package. That's why it's not working. You don't have leaps installed in your program.
Oh yeah.
That message says file and library leaps. There is no pack with the name leaps. There you go. Install. Yep. Yeah. Successfully. Yeah. That's fine. Now let's do it. Do it again. Now run your program. Oh, now you still need to. Yeah. recommend warning. It was under our version. Yeah, yeah. That's fine. That's actually, so now actually this warning that says, it's a warning, it's not an error. So just to everybody out there, there is a difference between a warning and an error. So a warning is not so bad. A warning is more like information and not a statement that it's wrong. So it's okay to have a warning that talks about linear dependencies, because it is very true that many data sets have linear dependencies in the data. That's okay. So this is okay. So you can continue. So your window's in front. I don't have my, but if you look at the, let's see, if you've got the slides.
Yeah, I have the slides.
Yeah, if you go ahead to the next command line. Yeah, that looks familiar. Yeah. Yeah, and then there'll be another, yeah, that's right. Yeah, that looks correct. That looks familiar. Yeah, okay, great. And then before we go to the next command, let's just take a look at this, and then you go to the next command. So this is a little fun little chart. Do you understand what this chart is showing, Milal?
Not really. Some
Okay.
stars.
Okay, so it's a matrix. And so we have the names of the variables across the top. And on the left is how many variables do we want in the model? So we have 8 models here displayed in this matrix. The first row is 1 variable. The next row is 2 variables. The next row is 3 variables. And for each number of variables, which variables has Leaps told us should be in this model?
Oh yeah, this
So
one.
this is a very basic, piece of information. So if I want a 5 variable model, I should go to row 5, and the columns with a check mark in them are the variables that Leaps recommends that I put in that model. So it's very introductory, right? We don't even know what the R squared of these models yet are or anything. It's just a very introductory piece of information. But now go ahead to the next command.
Sorry, what?
Go ahead to the next step.
Okay.
I believe it, did I have, yeah, that's right, the plot step. Yep. I have not researched this command in detail. I'm just copying it directly from the manual that I got it from. But I believe the scale command is a command where you can pick what the measurement is, and the main command is just cosmetic. The main command is just a title for the plot. And so over there on the right is the plot. Can you open that window up and make it bigger? Can you? Yeah, that's perfect. All right, so this is not Space Invaders. This is not Tetris. This is this is a graph. And so down on the bottom is the variable names, and on the left, on the vertical scale, on the little rat scale here is the R squared value. And for each level of R squared, we see here which variables Leaps is telling us should be in the program, should be in the model. So at an R² value of 0.8, there is a model that has these black, right, exactly, has intercept, county population, num lanes, width lanes, access control, foundation class, truck route, but not locale, and FC1, FC2. And that's how you read this. So you have a graphical picture here, and you kind of get a sense of, okay, what is my trade-off between complexity and R²? And you can see quickly in this picture which, the more black there is, the more complicated your model is, because the more variables it has. So what you really want is a lot of white space and a very high R². And so you look down this model. So we could say, okay, well, at the very top of this picture, there's a model that has 1, 2, 3, 4, 5, 6 variables with an R² of 0.81 something. We don't know. It's the number is shortened on the left scale here. But we could delete the variable width lanes and have 1, 2, 3, 4, 5 variables and still have an R² in the same rough dimension. And we could go even further down and have a variable with 1, 2 county pop, num lanes, access control, and FC1, and that would still put us in the 0.81 category. And in fact, I believe that is in fact the model we just finished with before the pause, before the coffee break. I believe this one in the middle with lots of white space, like the third one down from the top, I believe that is in fact the one that yes, it is. See, there it is. You can see it right there. Malal is pointing to the text in his window, in his console window. So you can see that. So you see the relationship here. Stepwise got it really quick from the first step, but what the subsets is doing is giving us more information. Subsets is giving this graphical picture that says, well, if you don't like this one, I got another model over here with leather seats and a stereo and analog brakes, that's about the same price. How do you think of that? And that's what's going on here, is that maybe this picture would give you some other ideas about what you might do. But at the moment, from the picture and from the previous result, I think our previous result was pretty darn good. And what this picture does not tell you, we do not have any information on significance. So, and honestly, that's just where I ran out of energy. I don't know in the Leaps package what the command is if I wanted to get that information. It's probably there somewhere, but it's unfortunately, in my Google searching and my preparation for this lecture, I did not find that Leaps was especially popular. It seems a little bit older, and it already seems to be something people are switching away from. So, but I wanted to demonstrate this graph is really attractive. So I thought we wanted to look at this graph. So great. Anybody else have any questions or comments on this before we go to the second method?
Why are some of these gray?
I do think, this is where I couldn't find any documentation. I do think maybe the color has something to do with significance, but I don't know.
Okay.
I think it could be. I'm not sure. I really don't know why they're gray. Clearly those are less desirable models. The R² is 0.58. So I'm not clear what the color is trying to tell us, and I didn't find any documentation for that.
Okay.
In my investigation, but clearly there is a pattern there, and that happens over and over again. This color change at the bottom of the scale is intentional. It's clearly an intentional piece of information. The other thing that I don't talk about a lot is the intercept. So the intercept is the fixed, is the beta null value in the regression. And I don't talk about it a lot because it's pretty rare. It's pretty rare to have a regression model where the intercept is not included in the model and it's not significant. It can happen. It can happen, but it doesn't happen very often. So when we say how many variables are in the model, some people count the intercept as one of those variables. They say, oh, well, the intercept is one of those variables too. And then when you look at the sum of squares in the ANOVA table and the p-value calculations, it is included in the math for those calculations. But when I'm thinking about my model building, I don't in my mind think of the intercept as a variable. It's not a variable, it's just always there, except for when it's not. So I don't really look at that too seriously. So I don't consider that, and when I'm thinking about my model building, it's not something that I care a lot about. But once in a while, not very often, but once in a while, the intercept is not in the model, is removed as significant, which kind of sounds weird, but it is. So let's see. Next, any other questions? Anybody? And then I'll put the slides back up. Put the slides back up here. All right. Now, so where were we? Let's see here. All right. So we just did that. Come on. There we go. Come on. Yes. All right. We did that. We did that. We did that. Did I forget anything? Nope. I got it. I did that. I did that. Oh, okay. So I'll just jump to this, right? So to actually get the details on the best model, and I say I put best model question mark because this LEAPS package didn't tell me which model is the best. And I mean, it told us which one has the highest R square, but that it didn't tell me anything else. And so which one is the best model? Well, let's just assume that R squared is our goal here. So I picked the model at the top of the table and said, I want the one with the highest R squared. Here is that model. And I had to manually type in the variables and run the model and get the analysis. So that's a 8163 R squared. We were at 8121 previously with the stepwise. So we're talking small change here, and we're introducing a bunch of variables that have really bad p-values that are not significant. So I think there's a strong argument that this model, even though it gives a higher R squared, is not something I would really feel comfortable presenting as the best solution or the best analysis tool. And this is, as I've said before, this is a concern that people who are not well trained in these areas might be tempted to pick this model and present it and say, hey, yeah, this is it. This is the model we're going to use. And I would not do that. I don't agree with that. Let's see here. And so we have another method. So here's another method. So here's our second method. How are we doing on time? I think we're going to be great here. I think we'll have a break here in a few minutes. I'll have so here's our second method. This is a different package called GL Multi. And this package has more support, has a more detailed documentation, and it shows up more frequently in articles and in references. So this package seems a little more powerful and seems a little more popular. And it has more functions. It has more options you can type in as well. So here's the code. It also requires something called RJava. So when you go to install it, you may get an error that says, I need RJava. And so you have to go install RJava first and then install GL Multi. And then, and that, that takes a little bit of time. So maybe,
Stephen?
Yes.
When I try installing RJava, it comes with an error and says error package or namespace load failed for RJava.
And you got it. Are you doing it from the menus?
I'm doing it for the menus, and I even tried installing it with the code directly, and it doesn't work.
I had a similar kind of error. I had an error the first time I installed it, and then I quit R and reopened it, and then did it again, and I think it somehow worked after that. Try that now. Quit R and then relaunch it, and then.
Oh, I'm trying.
Yeah. I also had a kind of an odd error message.
It's the same error.
Yeah. Do you want to share your screen? I'm curious to see what it looks like.
Sure. Just comment out some things. There we go. Right windows. It's probably small. There we go. And when I try the library RJava for accessing it just says this and the same when I go into the GL multi. That's a run.
Do another thing that you should do. Have you run update on your packages?
I just installed them.
Yeah. So this is again one of the joys of this kind of software. And you know, so the one you install very often is not the most recent version.
Okay.
Does that make sense? Do you like that? So there is an update packages command, and you should call update packages everything, and it's going to go through a long list of packages.
So just like that, I'll just
update everything. And this is probably a good moment. We'll probably take another pause here because I think more than one person here probably should do that. Run update, install these packages, debug.
But should I write anything in the update package? Let's see,
well, on my standard R console, it's a menu item. I don't have to do it. I don't have to do it from the keyboard.
Okay.
So I don't know what the text command is. But in the it's check for package updates. That's it right there. Select all, and you can see it's a lot. Yeah. So yeah, let's just update a few things. No problem. Just the whole damn installation, but but that's very common. And I am actually frustrated because I'm on a DTU computer and there are security limitations to what I'm allowed to edit. And some of my packages can't be updated because the DTU security prevents R from accessing the drive. So I've just lived with it. And so far it hasn't stopped me from getting my work done, but it might stop me later if something is, bad. But anyway, and you may have to run this more than once because, it updates and then that creates a cascade of other updates. And then you got to update it again. And then you may have to restart R and then, but yeah. But hopefully once you've updated it, and installed once, you won't have to worry about this for the rest of your education.
hopefully.
But this is very typical, right? And we see this with Microsoft Windows, for example. If you reinstall Microsoft Windows on a computer, the version you installed immediately needs to be updated. So it is what it is. So actually, I think maybe this is a good point for another break because so everybody on the call here, everybody in the meeting, check your updates on your packages, install R Java, install library multi, GL multi, and then maybe even go ahead and give a try at this code and then we'll come back from break, and I'll quickly run the code on my console and show the solution, and maybe we'll get out of here at a reasonable time. So let's take another break now, 10 minutes, and I'll see you back. I'm going to set my timer. Here we go, and we are on break. See you back in 10 minutes. All right, so welcome back. So this confet size, the manual says it does one thing, but it doesn't do what I think it should do. The manual says that this will say generate this many models in the solution. And it does under a different setting, but when I have this method L, it seems the confet size is ignored, because when I do this method L, I get 100 solutions. So I'm just guessing it's a software bug that this confet size argument only works under certain other settings. And some of these aren't absolutely necessary. Some of them, the default values are probably fine. I just wanted to make sure it worked according to the guidance I was using. So let's see. Yeah. Good. That looks correct. There you go. So that is correct. Everything looks good. And then it says at the bottom there were 50 or more warnings. And I'll be honest, I didn't look at the warnings. I don't know how important they are. They could be warnings like there's a linear dependency or something. I don't know. Let's take a look. I haven't, let's just try it. The model is giving me answers that look right. Let's see what. Oh, there you go. That explains why my confet size command is not doing anything. I guess that explains it. And I have to research more deeply to understand when I can use that and when I cannot, but apparently I cannot now. So that explains it. That explains why the confet size was essentially pointless, didn't do anything. Good. All right, that explains that. So let's see. Let's look at some information. And there's a lot of information. So what we're looking at here is a lot of stuff that isn't especially useful at the moment. But what this is here, this table is all of the AIC statistics for this thing it told us it fit 325 models, and here are the AIC numbers for all those 325 models. And then down here, I'm not sure, to be honest, what these weights are, but I believe these are the p-values for the models, which are all good. And then finally, here is what it recommends the best model should be right there. And so we want to get more detail about that best model. There you go. And so this gives us the full regression explanation for that best model. And we can see here that the solution that we got from the subsets in GL multi is exactly the same as the solution we got from the stepwise AIC. So that's good. That's not bad. They don't have to be different, right? I mean, so, but it kind of makes sense. It kind of makes sense because both of them are from the commands we entered. They are both using AIC as their decision. So if they're both using AIC as their decision, it kind of stands to reason that they would most likely both give the same answer. That's not a guarantee, because the stepwise method is going at it in one way, and this method is using a kind of fast surface search over the solutions. And it could be that they come to different answers. It's possible that they would generate different answers, even though they're both using AIC as the judgment method, because the statistic they're using is one thing, and the way in which they climb through all of those decision trees is another. So they might come with a difference. But in this case, for this data set, best subsets using GL multi and AIC gives me the exact same answer as stepwise using AIC, using that was from the MASS pack, from the MASS pack. So that's good. And, you know, that's not bad. And let me see, what did I want to show? Oh yeah, we can show the, yeah, let me switch to slides, because I have this already prepared in slides. So here's where we are. Here's a comparison between leaps and GL multi. So this is a comparison between the model we generated from leaps, assuming R squared was the best, and the model we get from GL multi, assuming AIC is the best. So how do they compare? Well, you know, that model from leaps has a little bit higher R squared. It has more variables, but out of those variables, only 2/3 are significant. Whereas the GL multi using AIC has a little bit smaller R squared, but it has 4 variables, and all 4 variables are significant. So it kind of gives you a sense of, how do these two methods compare? What am I getting from each of these two methods? And we can look then at some of the results. So here is, I've gone ahead and run the GL multi, but this will of course be the same, since the model is the same as our stepwise AIC, then this residual chart will be the same as we saw earlier. And the normality chart will be the same as well. Another little comment here, though, by the way, is that I didn't say before on the other model, on the stepwise AIC model, is notice where the outliers are in this normal probability plot. It should be said that one of the benefits of deleting those outliers from the data set is that it does significantly improve the normal probability, because the normal probability is violated most severely by the outliers here. And so that is another good argument for deleting these outliers from the data set and then redoing it, because this normal probability would improve after deleting these outliers. Because you can see they are way out on the tail here on these things, and is clearly affecting the data. So, but that's like, you know, that whole business, I don't know if we'll have time to do that. I thought we would originally when we started the semester, but things are just going a little slower than I thought they would. And it's a complete science, this business of how do you pick the outliers and what do you do. That is actually almost a lecture all by itself. So I don't know if we'll have time to do that. But I think it's safe to say that these automated tools that make recommendations are based on the principles that I would have taught if we had time, the hat matrix and things like that. So we'll go with that. So we're about ready to wrap up here. I think we're doing pretty good. I estimated 2 hours or so, and we're going to be on target. So we're almost done here. So some discussion here. We've tried a lot, but we've also noticed that the residuals and normality haven't really shifted a great deal as we've tried different things. And so there's a point where there's only so much you can do. There's a point where there's no magic way to just make the model better. It depends on the data. And you know, maybe some more transformations would help the data. There's some evidence in the residual plots that some more transformations would help. So more time could be spent transforming this data, improving the indicator variables, and maybe even considering some other transformations. And your book, this textbook, in my opinion, does not really cover transformations very well at all, actually. And I'm kind of disappointed. That's another thing I'm disappointed in. My old book from my university days has a whole chapter devoted to transformations with advice on how to do it and all kinds of things. It is another lecture. It is a lecture almost to itself. But the general rule of thumb, so what do you do? So it really comes down to look at the original scatter plot for the data, look at the residuals, and you look at those two charts and you look for patterns. And then based on those patterns, you experiment. You experiment and you try different transformations and just see if it makes it better. It is trial and error. It's not like there's just a magic guide that says this is what you should do. It is very often that you just have to try and see what happens. And from my old textbook from school, from college, these are some of the recommended transformations. So you look, and the figure on the left, what's on the left here is, this is a shape that you might see in the residuals. You look for this shape in the residuals. And if you see this shape in the residuals, these are the transformations that are recommended. And you can see that there's more than one choice, right? So we see a curve like this, and the choice could be square the X data, or the choice could be get the exponent of the X data. And which one? You just got to try it. You know, there is no exact answer as to which one. You just got to try one and see what it does. And for this shape, it's recommending, you know, a log 10, or it's recommending a square root. So there are, you know, different possibilities here to experiment with this. And let's see, what else was I going to say? No, yeah. No, that's it for that slide. But these are just examples of things that are typically done. And we haven't even gotten into cross effects. We might have time to get to that later. But that is what happens when two variables work together, when they multiply together. And then you can also transform the Y data, the output, the dependent data. So, and again, you look at the residuals. If you look at the real difference here, notice that when it's an X transformation, the variability is pretty much the same in the residuals. You see this band, this kind of band of data here. Notice the band is pretty constant. So that kind of implies an X transformation. If the band is diverging, if the band is changing the width or shape, that kind of implies you might want to tinker with the Y variable. You might want to tinker with the Y variable. So these are recommended transformations for the Y variable. And, you know, which one? Try one. There's no, yeah, you just got to try and pick. But these are some suggestions on modifying that. I do believe this figure is in order. So this is A, this is B, this is C. So this transformation is intended for this figure, and this transformation is intended for this one, and this transformation is intended for this one. It's a little graphical error on there. Was there a question? Yeah, okay. So those are some of the recommendations, and you will see already an example of the impact of a transformation in your homework exercise, because that's part of your homework. But there are many ways you can do this. There are many ways you can do this, and you look for clues in the residuals. The residuals are so important. Residual figure is so important to understanding what's going on with your regression model, and then applying a transformation based on those residuals. So we're about done here. We're done. So some closing comments. Yeah, it's really surprised me how much what I thought would be pretty much an easy class to teach, just based on, hey, just teach them what I learned when I was in school. But there has been a lot of change in the last 15 or 20 years. There's been a lot of change, and it's really surprising. When I studied this as a student, there was basically 2 or 3 choices for software. And in reality, there was really only one choice, because the other couple of choices were just not competitive. They weren't really serious competitors. That one choice was SAS. I mean, SAS had the market locked for a long time as the only statistical software package. And then a little bit of folks using SPSS, and the folks using SPSS were in a different field. They were people in social sciences and stuff, and they were like in a whole different area. So it was really SAS. I mean, SAS was it. SAS was the tool everybody used. And now it's exploded. You know, we still have SAS, but now we have R, and R is not one package. R is just a collection of lots of other packages. And that makes it a little complicated because some of these packages duplicate each other, like Leaps and GL Multi. I mean, they kind of duplicate each other. They kind of compete with each other. They're both developed by different authors as their own voluntary work. So what ends up happening is every time some academic, well, there are 2 things happen. One, a new package gets developed because somebody says, I really need this package, and the features in the other package don't do what I want it to do, and so I'm going to make a new package. Great. The other reason a new package gets developed is because you make the new package, and then you write a paper about it that gets published. And as an academic, this counts as part of your work output in your job. So there's a little bit of an incentive in academia to create more packages, because you get credit for it, because you don't get credit for writing a long email to the author of the original package and saying, hey, I found all these things that need to be fixed. Let me help you fix it. But you do get credit for starting from the beginning and making a new package and publishing it. Now that goes on your CV, and now you get credit at your university for having written a paper, and it goes into your promotion package. So there's a little bit of a disincentive here for quality control and for simplicity, because it encourages more separate packages and more separate unsupported software. So it makes a course like this actually a little more difficult to teach and a little bit more difficult to create clear lessons that have a real direct beginning and end, because the software we're using has so many choices, and and there are many different options we can look at in using the software, especially if I want to teach a class that's not about software, right? I mean, this would be different if we were over at DTU Compute and part of your education was all about programming software, and you were really excited to learn about how to program software. But that's not really what we're about here. That's not the deal. We just want some good tools that work and then generate solutions. So it makes it a little more challenging. We could always switch back to SAS, but then that creates access problems in terms of we don't have a really conveniently available SAS license, I don't believe, that can just be given away to private computers, and other issues there. But anyway, so we're done. Glad that we had a little bit shorter lesson today, so that you have some time to kind of get started on the homework exercise. And again, I hope it's well described. I hope it's pretty clear, and it should be pretty much using exactly the same code and models that we have just done today in this lecture. So it should be pretty clear how to do that. So I hope it's not too bad from an exercise, from a workload point of view. So,
Stephen, if we still have a problem with the Java, mine, it keeps saying there's a loading requirement package and there's an error when I unpackages. I've uninstalled and installed the new one, and I updated everything several times, and it doesn't seem like there's anything left to update, but there keeps coming a fail with the R Java.
There are two choices. One, it's possible to do the homework assignment without the GL multi package. So the one choice is you don't do it. You just give up and say the heck with it. The second choice is, you Google it and Google this error code and look for a result and, the whole 9 yards, restart the computer and, reinstall this and, there's no easy solution. It's unsupported software, right? So I had quite a few in preparing this lecture, I had quite a few different things where I had different things that didn't work or error messages that I was like, what the heck is going on now? And the solution was to Google it, was to grab the error code and the name and R or the name of the package and Google it. And then results would come up from Stack Exchange and from various help forums and things and you would find somebody else reporting the same problem. And then you would kind of dig through and try to find if one of the solutions worked for you. And some of the solutions are easy to understand. And some of the solutions are written by guys who are like computer geeks or computer programming professionals. And they just start going off and talking about stuff. I have no idea what they're talking about. So, so you kind of have to poke around. So those are the two solutions. The homework assignment says,
I can see question 4, you use GL multi, and then question 6, you have to discuss question 4.
yeah, but question 4 says you also could use leaks. So it's possible to do question 4 with just leaps. But ideally, I originally wrote it to use leaps, and then I found GL multi the next day. And then I decided, yeah, GL multi looks better. I like GL multi better. So I rewrote the question and said, hey, maybe GL multi is the way to go. And then there are other packages, there are other tools. So I haven't had the time to research any of them, but there are other packages, but that's just more burden and workload on you to investigate that. But GL multi seems pretty popular. So I guess the thing is, what's the story about this R Java? Why it's not wanting to load or what's going on there? But yeah, it's a bit of a tech debugging exercise. But that's my advice for now. If you don't have it, if you can't get it to figure it out after like 2 hours, I would just say, okay, fine, just use leaps and just forget the GL multi for now. That's what I would do. Yeah. All right, guys. Anything else? Good. All right. Well, have a good weekend, and I'll see you next week. And I'm going to take a look at the learning objectives for the class. And I have a feeling that logistic regression is our next agenda item. And hopefully it'll go a little faster, because this is the core. What we've just done is really the core of the course. And these other things are kind of just built upon what we've already done. Logistic regression and Poisson regression and all kinds of stuff, binomial. These are just another flavor of the same thing. So hopefully those lessons will also be pretty pain-free. So, all right. So good weekend. I'll see ya. I'm signing off. Bye-bye.